In this reaction, we're reacting an alkyl halide with potassium hydroxide in an alcohol solvent. It's pretty easy to tell that this is going to be an elimination mechanism. We're just going to expel the halogen, and we're going to develop a new pi bond between two carbons. But there's a little bit of a tricky exception here that we're going to have to apply when selecting the correct alkene. So let's go ahead and look. There can always be two major products here because we have two carbons attached to the carbon with the halogen. So let's look at them now. The first one we have is when new pi bond is going to form on the more substituted carbon, tertiary carbon. And here, I'll go ahead and make that a different color too. So if we consider this product, it's the one that people are more likely drawn to because this would be following Zaitsev's rule. If we remember, Zaitsev's rule states that the more conjugated alkene is going to be the more stable product because of hyperconjugation. And that is where the hydrogens attached in methyl groups can provide some sort of electron density, further stabilizing an alkene. Whereas for the other pi bond, there's only going to be two carbons connected, making it appear that that alkene would be less stable, and thus a minor product. But let's look a little bit more closely. So let's draw it out right now. If we have our alkene, our new pi bond formed right here, you might realize that there's actually a resonance structure that can follow. If we want to go ahead and rewrite this benzyl ring, we can see that there's going to be a delocalized network because this carbon is allylic, which means that it's placed one carbon away from a delocalized system or a pi bond, which is going to enable it to participate in a resonance structure. Now, while Zaitsev's rule typically follows because it enables the formation of a more stable alkene because of hyperconjugation, you have to remember, hyperconjugation is not nearly as stable as resonance structures, where overlapping p orbitals enable greater stability of the product. So, with this reaction, while it may appear odd, the major product is actually not going to follow Zaitsev's rule, and in fact is going to be the one that doesn't follow the proper rule. But it's exceptions like these that make the rules, because we can see that this pi bond leads to increased stability in the molecule. That's why chemistry is always important, to look at the entire mechanism. You have to consider the molecule overall, and not just get caught up in shorthand rules, because there are exceptions that break them.